We're going to learn how to solve simultaneous equation using matrices. Okay, now the bigger a system of equations gets, the more useful using matrices is. So we're going to start small at 2 by 2, but in the future you'll see that this has huge benefits. Okay, so perhaps this is no quicker than solving two equations and two unknowns with things you know like elimination and substitution. But as we get into bigger things like 3 equations and 3 unknowns, and beyond, you'll see that this has huge benefits and it's quite programmable too, if you know what I mean. So we start with a little matrix equation. So matrix A times matrix X equals matrix B. So we have a 2 by 2 times our column matrix times equals another column matrix B, and if you did the work, that would provide you with a system of equations. So verify this yourself, but you've got two equations are generated by doing the math in these matrices, by multiplying them out. You can check that yourself. Now, linking to our previous work, we're going to undergo this series of steps. We're going to times A pre-multiply it by its inverse, which means on the other side we need to pre-multiply B by A inverse as well. This will mean we get the identity matrix I2 times X equals A inverse times B. So X equals A inverse times B. That's an important result. So make sure you note that final result. Now, since for A, its determinant of A does not equal 0, it has an inverse. That's from our previous knowledge. So, in other words, it's invertible. And we can see that its determinant, actually, if you really want to be convinced, go ahead, you'll find that AD minus BC, you'll get 1. Okay, try it yourself. And if you do try it yourself, you'll find that to get A inverse, you'll have the matrix -3, 2, -5, 3. Again, you can verify that yourself. So using the last result there in orange, to get X, we need to pre-multiply B by A inverse. So let's do that. And B was 5, 9. And to cut a long story short, you'll get the matrix 3, 2, a column vector or a column matrix. Now if you go back and look at the form of X back up here, there's X. Okay, X has two elements, little x and little y. They're the solutions to the equation, to the simultaneous equations there. So you can try it yourself. Why don't you try it? There's ways you can try it. Easiest way is to substitute those values. You can graph on your graphics calculator, get the intersections, or use Desmos. You can do the whole elimination or substitution, solve it yourself, and you'll get the same results. So all that's left is for us to write, therefore, the solutions are X equals 5 and Y equals 9. So we've solved it. The only issue is, what if we have something without a unique solution? You have a system of equations with no unique solution. Now that means it could mean a couple of things. It could mean the two lines are parallel. Now you know they don't intersect, and therefore they have no solutions. So that means it doesn't have a unique solution, it doesn't have any solution, and it could be the same line, okay? That's a problem, because it has infinite solutions. It intersects everywhere. It might not look like the same equation, but if you times every term by the same constant, you get basically the same equation. So what if that happens? So what does that mean? We know what that means in terms of the algebraic way of approaching it. What does it mean for the matrices? Here's an example. We have the line x plus 2y equals 3 and negative 2x minus 4y equals 6 in red and blue respectively. And as you can see, they're parallel. So what gives? So putting them down here in y equals mx plus c form, you can see that they've got the same gradient, but the y-intercept varies. So one's translated compared to the other, same gradient, so that means they're parallel. Well, we talked about invertibility before, and we need to use the determinant. So the determinant determines whether the inverse can be found. This one doesn't have an inverse. We need to find determinant A. First thing we need to do is identify matrix A out of all that. Remember, it was the coefficient matrix, so that was 1, 2, negative 2, negative 4. It's the coefficient matrix. Did you notice that earlier on, that matrix A is the coefficient matrix? Go back and have a look. So back up the top, when we saw 3, negative 2, 5, negative 3, 3, negative 2, 5, negative 3. So where A is the matrix of coefficients of the terms, the x and y terms. So interesting. Thus now we can determine the determinant, and basically we've got A times D, which is negative 4, minus negative 4. So that's 0. So we know that when the determinant is 0, there's no inverse. Okay, no inverse. And the conclusion means there's no unique solution. So that's about the only complication with this with 2 by 2s.